we've seen a few examples of rings now, and I want to take a minute in this video to look at why that definition is so important and why we have those 7 properties and not other ones that we're familiar with. So it turns out, and this is all talked about in remarks 2.8 in your that just those 7 properties are enough to get lots of other results that we're familiar with. So if we just use those 7 properties of a ring, we're going to get some other things that follow. So first one is this kind of cancellation of a's on both sides of this equation. If I have a plus b equals a plus c, then I can conclude that b equals c. This is certainly something we do all the time. This is why we can do algebra, right? Subtract a from both sides. So if I want to see that this follows from the definition of a ring, I need to use only those pieces of the definition. So if I start with a plus b, and I'm doing a little proof here, equals a plus c, then what I can do is add something to both sides of that equation. And what I'm going to add is minus a to both sides. So as long as I add to both sides, I have the same, the 2 things are still equal. So now I have minus a plus b is minus a plus c. All right, and from there I'm going to start using ring properties. So minus a plus a, that was part of our definition of a ring, and that is 0, right? So I'm going to replace that. Same deal here. I have minus a plus a, that's just 0. Okay, so that's using a piece of the definition of a ring. And now I'm going to use another piece. 0 plus b, we have a piece of our ring definition that says that's just b. Same for 0 plus c, that's just c. And that's the end of our proof. So I know I can do this kind of subtracting a from both sides to conclude that b equals c. All right, our second result here is that for every a, there's a unique b in R so that a plus b equals 0. So this is talking about additive inverses, but the thing that's new is that uniqueness. We haven't talked about that yet. What we want to do is say, well, what if there are actually 2 things that are additive inverses of a? And this result is saying, no, there's not. There's really only 1. So to prove that there's really only 1, we're going to do this little trick where we say, suppose a plus b is 0 and a plus c is 0. So both b and c are additive inverses. Then I want to be able to conclude that b is equal. Okay, and I'm going to do that by relying on that property that I just showed. So what I know is if a plus b is 0 and a plus c is 0, then a plus b is a plus c. So by number 1 above, b equals c, and that's it. So doing this, showing that there's a unique additive inverse, is what lets us give it a name. If there were multiple additive inverses, we couldn't give it its own symbol of minus like this. So saying there's only 1 of them means I can give it this name. I can call b just minus a. All right, next one. 0. So multiplication by 0 wasn't mentioned at all in the definition of a ring, but it turns out that the definition of a ring still tells us that a times 0 is 0, and 0 times a is 0. So we're going to prove this in a little bit of a weird way. So I'm going to say, I don't know what a times 0 is, but let's do a times 0 plus a times 0. Okay, I don't know what it is, but I'm just going to add it to itself. What this lets me do is use the distributive property. So that's one of the properties of a ring that I'm using right here. I'm using the distributive property of a ring. Okay, and then anything plus 0 is just that thing. So a times 0 plus 0 is a times 0. Okay, so that right there is using that addition by 0. That was the additive identity property. All right, now, once I've written all that down, look at what I just showed. I showed that a times 0 plus a times 0 is equal to a times 0. I'm going to pull out another little ring property here and say, well, the a times 0 on the right-hand side, that's the same as a times 0 plus 0, right? 0 is the additive identity, so I can add it anytime I want to. And now we've set ourselves up to use 1 again. Look, I've got something showing up in both of those places. So this a times 0 thing plus a times 0 is a times 0 plus 0. And so by property 1, I know that this, the right-hand summands here are equal, that a times 0 is 0. All right, these little proofs are strange. It feels sort of like you're not doing anything or you're just writing down things you know over and over again. But if you listen through this again and write down what ring property I'm using at each step, you'll start to see that we're really using only those properties to come up with all these facts that are familiar to us. All right, here's one more. So we're going to do 2 more total. So for every a, minus 1 times a is equal to a times minus 1, which is equal to minus a. This, again, looks like maybe it's not saying anything, but we're going to think about this carefully. So this is talking about a product of 2 numbers, right? Minus a, that's not talking about a product of 2 numbers. That's talking about the additive inverse of a. So what we're saying here is that when I multiply a number by -1, that gives me the additive inverse of a. All right, so to prove this, what we're going to do is we're going to take a times -1, add it to a, and our goal is to show that here what we get is 0, because that's what would tell you that the first thing is the additive inverse of the second thing. All right, if I want to do this, I'm going to take a times -1, and I'm going to do something kind of similar to the last trick and set this up so that I can use my distributive property. So first I'm going to say I have this multiplicative identity 1. I can multiply a by 1 anytime I want to. It's just a. And then I've set myself up to use that distributive property, a times -1 plus 1. -1, that's the additive inverse of 1. And so -1 plus 1 is 0. So now I have a times 0. And by the property I just proved, I get 0. So this a times -1, when I added it to a, I got 0. And so it is the additive inverse of a. All right, so that's a useful thing. And what this means now is we can start to be sloppy about this. We can move signs. Multiplying by -1 is just making additive inverses. We can just use signs and sign changes the way we're used to. All right, and now one that always comes up early in people's education is the product of 2 negative numbers is positive. And why? This is always a little bit of a mystery, I think, for people when they first hear it. But here's why it is. It's all based on those ring properties. So we're going to prove this by thinking about times minus b in light of the above results. So minus a, we know now, is just -1 times a. That's the additive inverse of a, and I can call it -1 times a by that previous property. And I can do the same thing for b. So my minus b is really -1 times b. And then I'm going to group a little differently. So this a times -1 inside here is now just minus a, right? So now I have -1 times -a times b. And now -1 times -a, that should give me the additive inverse of minus a. And the additive inverse of minus a is unique, and we know what it is. It's a, because a plus minus a gives me 0. So now this, negative 1 times negative a, is the additive inverse of minus a, which is just a. And so now we're down to a times b. So these ring properties are the reason why the product of two negatives gives you a positive. In any ring, that's going to be the case, which is kind of a cool thing, because that ring definition really didn't say a whole lot about negatives, but this is where that comes from.